Hey guys, in this video we will be talking about the rules of exponents. Okay, so let's start with defining what an exponent is. Suppose we have the following expression. Here we have 5 factors of the same number, 2. Repeated multiplication can be written in a more compact way called exponential notation. Here, 5 is our exponent and 2 is our base. So the base of an exponential expression is the repeated factor, while the exponent is the number of times that the base is used as a factor. Let's evaluate some expressions. For part A, we have 3 to the 4th power. So our base is 3 and the exponent is 4. Therefore, we will have 4 factors of 3. And this multiplies out to 81. For part B, 2 to the 1st power, 2 is our base and 1 is the exponent. Therefore, we will just have 1 factor of 2. So 2 to the 1st power is just 2. This will be true for any number raised to a power of 1. It's the same as writing the number itself without the exponent. For the next part, we will need to be careful when identifying the base of the exponential expression. So for part C, our base is -4, but for part D, our base is actually just 4. Only 4 is being raised to the power of 2, and the negative is left on the outside. So for the first expression, we will have 2 factors of our base, -4, whereas for the second expression, we will have 2 factors of our base, 4, and then we just bring in this negative that is on the outside. So to simplify the first expression, we will multiply -4 times -4, which is +16. And the other expression will simplify to -16. So an exponent has the same meaning whether the base is a number or a variable. For example, if we have x to the 4th, x is our base and 4 is the exponent, so we will have 4 factors of our base x, which is the same as x times x times x times x. So exponential expressions can be multiplied, divided, added, subtracted, and raised to powers themselves. Let's start with multiplying exponential expressions with the same base. Suppose we have 2 to the 3rd times 2 to the 5th. For the first factor, we have a base of 2 and an exponent of 3. Therefore, we will have 3 factors of 2. And the same applies for the second factor, where we have a base of 2 and an exponent of 5. Therefore, we will have 5 factors of 2 for this one. Now, if we look at this as a whole, notice that we have 8 factors of 2. And this can be written in exponential notation as 2 to the 8th power, meaning 2 to the 3rd times 2 to the 5th is the same as 2 to the 8th. And we can do the same thing if we had variables. So for the first factor, we have 4 factors of x, and then for the second factor, we have 3 factors of x. And then looking at this as a whole, we have 7 factors of x, which can be written in exponential notation as x to the 7th power. Therefore, x to the 4th times x to the 3rd is the same thing as x to the 7th power. So if you haven't noticed, there's actually a shortcut to this. You can actually get the same answer by simply adding their exponents while keeping their common base. This property is known as the product rule of exponents. So if we have 2 exponential expressions with the same base being multiplied together, like a to the m times a to the n, and if the exponents are positive integers and the base is a real number, then a to the m times a to the n is equal to a raised to the m plus n, where you just simply add the exponents and keep the common base. So let's try a few examples. We want to simplify the following expressions. And since we are multiplying exponential expressions with the same base, we can actually use our product rule. So we will keep our common base and just add the exponents. And this will give us 4 to the 7th power. And for now, we don't have to evaluate this, so we'll just keep it as 4 to the 7th power. For the second one, we can also use our product rule. This factor has an exponent of 1, so we can write this in if it helps. So this simplifies to y raised to the 2 plus 1 plus 7, since we're keeping our common base and adding the exponents. And this will give us y to the 10th power. For the next expression, we actually can write this without the parentheses, since this is all being multiplied out anyways. And if it helps, we can reorder our factors so that we pair up the 5 with the 3 and the x's together. So multiplying this out gives us 15 times x to the 3 plus 2, which is x to the 5th power. And exponential expressions can themselves also be raised to powers. So for example, if we have x squared raised to the 3rd power, our base here is x squared, and our exponent is 3, meaning we will have 3 factors of our base x squared. And now we can use the product rule on this. So we keep the common base and add the exponents, and this simplifies to x to the 6th power. And yes, there is another shortcut for this scenario. We can actually get the same answer if we just multiply the exponents. This is actually known as our power rule for exponents. So if we have an exponential expression raised to a power, and if our exponents are positive integers, and a is a real number, then a to the m raised to the n is the same as a raised to the m times n, where we keep the common base and we multiply the exponents. So let's try an example. For this, we will apply our power rule since we have an exponential expression raised to a power. So we keep the common base of 5 and multiply the exponents, and this simplifies to 5 to the 18th power. For the next one, we also keep the common base of y and multiply the exponents, and this simplifies to y to the 16th power. Now let's consider when the base of an exponential expression is a product. So for example, 2 times x times y to the 3rd power, all raised to the 4th power. This entire expression is our base, which is a product, and 4 is the exponent. So for now, let's expand this out using our definition of an exponent. We will have 4 factors of our base, 2x, y to the 3rd power. Since all this is one big multiplication expression, we can rewrite this without the parentheses. And we can also reorder our factors so that the 2's are next to each other, and so are the x's, and the same for the y to the 3rds. The 4 factors of 2 can be written as 2 to the 4th. The 4 factors of x can be written as x to the 4th. And the 4 factors of y to the 3rd power can be written as y to the 3rd power raised to the 4th power. And this simplifies to 16 x to the 4th, y to the 12th. Let's see if we can discover a shortcut method for a product raised to a power. Notice how each factor of our base was raised to the fourth power. So our power of a product rule is if we have an expression in the form a times b raised to the n power, where the exponent is a positive integer and a and b are real numbers, then we have a times b raised to the n is the same as a raised to the n times b raised to the n, where each factor of the base gets raised to the n power. So for example 4, let's simplify the following expressions. Since our base is a product raised to a power, we will use the power of a product rule and raise each factor of our base by the exponent 3. So 3 to the third power is just 27, and then we use our power rule here and multiply the exponents, and this simplifies to 27 x to the 6, y to the 15th. For the next expression, we do the same and raise every factor of our base by the exponent of 2. Simplify, and we get 25 x to the 4th, y to the 6th, z to the 2nd power. And the same for the last expression. It might be helpful to write the coefficient of -1 in for our base. So raising every factor of our base, we get -1 x to the 5th, y to the 15th, which is the same as -x to the 5th, y to the 15th. Okay, now let's see what happens when we raise a quotient by a power. Suppose we have a quotient like x squared over y raised to a power. Our base is x squared over y, and the exponent is 3. Using the definition of an exponent, we have 3 factors of our base, x squared over y. We can rewrite this as 1 fraction, and since we have 3 factors of x squared, we can rewrite the numerator as x squared raised to the third power, and the 3 factors of y in the denominator as y to the third power. And this simplifies to x to the 6th power over y to the third power. Now the shortcut of this is raising both the numerator and denominator of our base by the power. And this is the power of a quotient rule. So if we have a quotient a over c raised to a power n, and if n is a positive integer and a and c are just real numbers with c not equal to 0, then a over c raised to the n is the same as a to the n over c to the n, where both the numerator and denominator get raised to the n power. So for example 5, let's simplify the following expressions. Since our base is a quotient, we will use the power of a quotient rule and raise both the numerator and denominator by 4. Now we use the power of a product rule and raise each factor by the exponent. Simplify this using our power rule and multiply the exponents. And we get 16x to the 16 over 81y to the 20. We can also simplify exponential expressions written as quotients with the same base. So consider the quotient x to the 5th over x to the 2nd. We can expand this using the definition of exponents. The numerator will have 5 factors of x, and the denominator will have 2 factors of x. Now we can simplify this fraction and divide out common factors. We are then left with x times x times x over 1, which can be rewritten as x to the 3rd power. And the shortcut for this would have been just to subtract the exponents, 5 minus 2, while keeping the common base x. So our quotient rule for exponents is if we have a quotient with the same base, like a to the m over a to the n, then this is the same as a raised to the m minus n, where we keep the common base and subtract the numerator's exponent with the denominator's exponent. Okay, so for example 6, let's try to simplify the following expressions. Since we have the same base and this entire expression is a quotient, we can use the quotient rule to simplify this. We keep the common base -3 and subtract the exponents. This becomes -3 squared, which evaluates to +9. For the second expression, we can use the quotient rule on the common base of x and the common base of y. Subtract the exponents for x and y, and this simplifies to 2x to the 4th, y to the 1st, which is the same as 2x to the 4th, y. So sometimes a base is raised to an exponent of 0, like x to the 0. But what does this even mean? So let's try to give meaning to this expression. Consider the quotient x to the 3rd over x to the 3rd. If we apply the quotient rule and subtract the exponents, this will give us x to the 0 power. If instead we expand this quotient using our definition of exponents, cancel out the common factors, and this reduces to 1. Therefore, this must mean that x to the 0 is also equal to 1. So the 0 exponent rule says if we have a base raised to an exponent of 0, then it just equals 1. So let's apply this rule to the following examples. For the first expression, our base is 3, which is raised to an exponent of 0. Therefore, this expression simplifies to 1. For the second expression, this entire base is raised to an exponent of 0. Therefore, this also simplifies to 1. But for the third expression, only the base of x is raised to an exponent of 0. Therefore, just this factor simplifies to 1, and we have 5 times 1, which is just 5. And finally, what if we have negative exponents, like x to the -3? Let's give meaning to such an expression. So suppose we have a quotient x squared over x to the 5th. We can apply our quotient rule and subtract the exponents. This gives us x to the -3. Let's also try expanding the quotient by using the definition of an exponent. Then dividing out the common factors, we are left with 1 over x to the 3rd. So this must mean that x to the -3 is the same as 1 over x to the 3rd power. So this will be our negative exponent rule. So if we have a base raised to a negative exponent, we can rewrite this as 1 over a to the n, where the expression flips to the denominator and the exponent becomes positive. And if the base with a negative exponent is in the denominator, then this will flip to the numerator and the exponent becomes positive. So let's try an example. We want to simplify the expressions and write each result using positive exponents. So for the first expression, the base x has a negative exponent, and we apply the negative exponent rule to just x to the -2. It might help to write the expression as a fraction over 1 first. So the y to the 3rd power stays in the numerator, And we will flip the x and bring it to the denominator and make the exponent positive after flipping. So this simplifies to y to the third over x squared. Then for the second expression, the base of 3 and b are raised to a negative exponent, so we will need to flip these. So the a to the 6 stays in the numerator, and the 3 will flip and the exponent becomes positive. And the b will flip also and go to the numerator and make the exponent positive. So this simplifies to a to the 6th power times b to the 2nd over 27. And now just to summarize what we've learned, below is a list of our 7 exponent rules that we've covered.